Okay, hi guys. So today, obviously, hopefully you should have done the first bit on sketching quadratics and you found that fine. And this next little bit is optional, but like I said, it's kind of highly recommended. I think it's a really important thing that you learn when you're doing quadratics. And if you don't do it now, you're not going to do it till next year. And I think it's good to have that knowledge as you're going with sketching. So for every quadratic, there's two ways that it can be written. It can be written in what we call by the way, I should have mentioned, you don't have to write any notes for this today because it is optional. So just listen, I've got the exercise, but you don't feel like you have to copy anything down specifically unless you would like to. Okay, so we have what we call an expanded intercept form, and this is kind of the way that we generally write a quadratic, where you've got your x squared term, you have an x term, and you have a constant. Then we also have turning point form, and both of these, I'm going to show you on GeoGebra a bit bigger. Both of these give you the exact same quadratic. So if I put this onto intercept form, okay, here's our quadratic. You've got an x-intercept of -3, another one of -1. Now, if I superimpose this, that's f of x. If I superimpose g of x onto the top of it, now I've written this form as x plus 2 all squared minus 1. We can see that g of x perfectly fits f of x, so that gives you the same function, even though the equations are written differently. And hopefully what you'll notice here is f of x is written in expanded form, so this is the form of which from where we can factorize really easily. So sometimes you'll see this called intercept form, because that +3 on the end there, that gives you your y-intercept. And then also you can really easily factorize, two things that add to make +3, multiply to make +3, add to make 4 are 3 and 1, so therefore your intercepts are -3 and -1. So really easy to find your intercepts from expanded form. This factorized, or what we call turning point form of the equation, you'll notice here you've got a +2 and a -1. Now your turning point on this quadratic is at x equals -2, y equals -1. So that corresponds to the numbers that we have in here. So this form gives you the turning point. So there's a couple of advantages. So in your turning point form, you get the coordinates. I'm just going to write coords of turning points. You can also solve pretty easily from here, because if we want to find the intercepts, you make f of x equal to 0. So then you're solving for 0 equals x plus 2 squared minus 1. So we add 1. That ends up with x plus 2 all squared. You can take your square root, so we're going to end up with x plus 2. Now square root of 1 is just 1, so we're going to have plus or minus 1. And then we just minus 2 from that, so we end up with x equals -3, or x equals +1 minus 2, -1. Okay, so there are our intercepts. So you can still find the x-intercepts pretty easily from there. To find the y-intercept, obviously x equals 0, so then you need to solve for that one as well. Now your expanded intercept form, this is the general form that you'll see quadratics in. And obviously that one is probably slightly easier to go through and find your intercepts from that equation. And in that case as well, if you wanted to find the turning points, once you've got the intercepts, then you use the midpoint of those intercepts to find the turning point. Okay, now how do you go from your expanded intercept form to your turning point form? Well, you do that by completing the square. So if we know that our function is x squared plus 4x plus 3, okay, we complete the square and we put in our brackets, we've got x plus, now you take half of your middle term and then half of your middle term, okay, which is 2. And then we're squaring all that. Now remembering that you're adding in +4. So we need a -4, add 3. So therefore our function is x plus 2 all squared minus 1. Now obviously when your quadratic isn't nice values for the turning point. So you had a turning point at like -1.83 and 61.4568, whatever. that's not going to look as good in turning point form. So in that case, what you would then kind of go into is your intercept form, which is a much nicer looking quadratic when you can see your x squared, your x terms, etc., when you don't have integers. But turning point form, when you do have integer values for your turning point, is a really nice way of writing your quadratic. Okay, just one sec. Okay, the other nice thing about turning point form is how it relates to this idea that we call function transformations. Now, function transformations, I'm just going to scroll down a little bit. Function transformations is the idea that all functions have like a basic function unit. So, for example, for a quadratic, your basic function is just f of x equals x squared, because if we chuck that into our if we chuck that into our screen, we can look at the graph. We can see that it goes through 0, 0, and that it's kind of the most simple quadratic that you can have. Okay, so all functions have a basic form. Now, a basic form. Now, whenever you do something to that, then it's going to change slightly what the function looks like. And there's only certain things that you can do to a function. So, for example, and we've looked at kind of these already when we were actually doing functions. So if we look at this as a quadratic, if we've got f of x minus 1, okay, if we put this into our f of x, that gives us x minus 1 all squared. Okay, and if we go and we look at what this would look like, I'm going to put it in here. So f of x minus 1. Okay, we can see that moves, there's our equation, x minus 1 all squared. That moves our basic function 1 unit to the right. So it stays the exact same shape, but it's been shifted 1 unit right. So whenever you, and this works for everything, whenever you subtract 1 from an x value in a function, that creates a shift, or what we call a translation, of 1 unit right. All right. Conversely, if we add 1, so if we add 1, we can see we get a shift of 1 unit to the left. So that's x plus 1 all squared. So shift 1 unit left. Now what you should be able to see here is this is actually in turning point form. So if we say g of x equals to x minus 1 all squared, and if we imagine there's like a plus 0 on the end there, that's in our turning point form. So we would expect our turning point to be at the coordinates 1, because remember it's the opposite of whatever's in the bracket, 1, 0. And if we go back to that graph, we can see there that our turning point is there at 1, 0. So that's perfect. Oh, sorry guys, I don't know why my computer screen is just... Okay, so I just wanted to show a couple of other ones now. So these ones I've got in here. This is f of x plus 1, this grey one. So you can see that f of x plus 1, you've taken your f of x, so that's still your x squared, and you've increased it by 1. All the values, so that creates a vertical shift or a vertical translation of plus 1. You can also, for this green one, is x squared minus 1, so that's taking away 1. So you can see that when that 1 is now outside the x outside the brackets, okay, where you're just adding or subtracting 1 on, that just creates an up and down. So when you've got the plus 1 or the minus 1 inside the brackets, that creates a left or right shift. When you've got a plus or 1 outside the brackets, you get an up and down movement. All right, the next one that I want to look at is this one, f of 2x. So f of 2x, that creates 2x squared as a function. And you can see there, that makes it skinnier, it squishes it in. So f of 2x means that yes, it makes it skinnier. So that's because this is actually... I mean, if we were going to expand that out, that would be 4x squared as opposed to just 2x squared. Now that means that every time you are every time you're multiplying your x value by 4 to get your new y value. So it creates like this upward stretch, okay, what we call a dilation or a stretch factor. We can see here on the green function that originally when x is equal to -1, y is equal to 1. Now on the blue one, when x is equal to -1, y is equal to 4. So you've quadrupled what y is for every x, and that creates a stretch and makes it skinnier. For f of 2x, so 2f of x, we're going to have a very similar type of result, but it's not going to be as drastic. So in this case, we're not quadrupling x, we're just doubling it, because you're multiplying x squared by whatever that value out the front is, which just means that we're just doubling. So we can see here when x is -1, y is equal to 2. So it's still a stretch, but it's not quite as dramatic a stretch as it was before. These last two ones, I'm going to show you this one first. So t of x equals -f of x. So we've done -f of x, and that gives you -x squared. Now what this causes is a reflection. So the exact same function, but reflected around the x-axis, which gives you that reflection, that frowny face one. And we've already looked at that when we were talking about sketching earlier on. Really interesting one, which I like, is this one, -x squared. Now, if you take -x, now any negative number squared is just a positive. So this actually ends up being the exact same. But this is something that's quite unique for quadratics. So I'm going to show you a cubic, and then show you how it's different. So what are we up to? We're up to t. So let's go u of x equals x cubed. Ooh, too many x's there. Okay, so I'm going to u of x equals x cubed. I'm just going to turn these off. Okay, now I'm going to go v of x equals, I'll just go u of -x. Okay, so now if I do u of -x, you can see that what happens is we get still a reflection, but now it's a reflection around the y-axis. So you flipped it on the y as opposed to now in the x. Now, why didn't that happen when we have a quadratic? And well, I mean, the answer should hopefully be kind of obvious, and that is that a quadratic is symmetrical around the y-axis anyway. So even though you're flipping it, it's still the same thing. You end up with the same graph either way. All right, so I'm just going to write these in. Okay, so this one, vertical up one, vertical down one. This is a dilation factor 4. Now, what you'll see, what you might find next year when you do this, they might call it something different, because we're only looking at quadratics. I'm just calling it factor 4, factor 2. What you might see is this is a dilation in the x, or a horizontal dilation. This is a dilation in the y, or a vertical dilation. Okay, this one is a reflection about the y-axis. Axis. Okay, and this one is a reflection about the x-axis. All right, so you might be thinking, that's great, why do I care about this? And the reason why hopefully you care about this is because it'll lead into what we're doing tomorrow, which is looking at how, when you're given a graph, do you find the equation of that graph, what it would be. So for this, say for this one here, we can see here that we have the turning point is at the coordinates x is 4, y is 5. We can see it's an upside down quadratic. So from there we can start to build up maybe what it would look like. So we can talk about turning point form, and we can say that if we know that our regular quadratic comes through 0, 0, it looks a bit like this. Now what have we done to go from this to this? Well, we've shifted this quadratic 4 units to the right and 5 units up. So if we look at our 0, 0, we've gone 4 units, 5 units up. Now we also know it's an upside down quadratic, so that means it has to be negative. So we can start off and think that our equation is going to look a little bit like this. We're going to continue on with this tomorrow. I want you to have a go at the Google Forms sheet and just have a go at it like this. Just put in what the equation would be, or just select which one would be the right equation or what could be the right equation. And then tomorrow we're going to do it in a bit more of a sophisticated way. All right, thanks very much. Bye.